Welcome back to educator.com. Thank you for joining us. This is linear algebra, and today we're going to continue by discussing cofactor expansions and using the cofactor expansion of a matrix to compute determinants and to also compute the inverse of a matrix. Now, we did talk about the inverse of a matrix last time, and although this particular procedure that we're going to show you today with cofactor expansions and something that we define in a minute called the adjoint, it is theoretically useful. Computationally, it's not something that you want to use for more than a 3x3 or a 4x4, but again, for theoretical reasons, it's always nice to be introduced to it and to see how it functions. So let's just dive in right now. Okay. Let's start with a definition. As always, we will let A be an n by n matrix. And we will let M, capital M, sub ij be the n minus 1 times n minus 1 submatrix. And again, these definitions are more for formal purposes. Once we actually do examples, anything that seems a little strange and unusual here will make a lot more sense. Of A obtained by deleting the ith row and jth column. Now let's see, so let A be an n by n matrix, let M sub ij be the n minus 1 by n minus 1 submatrix of A obtained by deleting the ith row and the jth column. Now the determinant of this M sub ij is called the minor of the entry A sub ij. So for example, if we had A sub 3, 2, that would be the third column, second entry. We would knock out that row and that column. We would take the determinant of what was left over, and then that's called the minor of that particular entry. And again, we'll do an example and it'll make more sense. One more definition. The cofactor of A sub I, let me put an I there, of ij, which we denote capital A sub ij, so cofactor, we use the capital, minor, we use the M, is the following. A sub ij equals -1 raised to the power of I plus j times the determinant of M sub ij. Okay, don't let all these subscripts and i's and j's and -1s scare you. Let's do an example and it'll make a lot of sense. So let's define our matrix A over here. We'll have 3, -1, and 2. We'll have 4, 5, 6, and the third row will be, oops, excuse me. We'll do 7, 1, 2. Now, M12, so M12, this is the submatrix that we get from crossing out the first row, second column. So if I knock out first row, second column, I'm left with 4, 6, 7, and 2. So we have 4, 6, 7, and 2. And that's exactly what it is. That's all this means. First row, second column, go back to the original matrix, cross out, and the numbers that you have left over, those form the submatrix, in this case 2 by 2, because the original was 3 by 3, so it becomes, remember, up the definition n minus 1 by n minus 1. 3 by 3 becomes a 2 by 2. Now, if we take the determinant of this M12, and again, the determinant of a 2 by 2 matrix is just, let me put some parentheses, is just that times that minus that times that. So it's 2 times 4 is 8 minus 42. What we end up with is minus 34. So let's put that aside for a second. So we have the minor, we have the determinant of the minor, and then we have that other thing that we defined, which is the cofactor. Well, the cofactor of 1, 2 is minus 1, and the power that you raise it to is the sum of this 1, 2 right here. So it's 1 plus 2 times the determinant that we got, M1, 2. Now, minus 1 to the third power is minus 1. So it's minus 1 times, and the determinant we found already, which is minus 34. So our cofactor is 34. So let's go through this again. We have a matrix, we have a minor, we have the determinant of that minor, and we have something called the cofactor. So our matrix, this is our original matrix right here. Let me actually use, so this is our original matrix. We decided to take the minor, the M1, 2, which means cross out the first row, the second column. So we crossed out the first row, the second column. What we were left with was a 2 by 2. That's our minor. It is a matrix. When we take the determinant of that minor, we actually end up getting this number right here. So this is a number. When you take a determinant, remember a determinant actually gives you back a number. And then what we do is we find the cofactor. The cofactor, 1, 2, is the determinant that we got multiplied by negative 1 raised to the power of the sum of the indices, 1 plus 2. Let's do another example. Let me go back to my, actually let me go back to blue ink here. So let's see. This time let's calculate the M23 minor. So when we go back to our original matrix and we knock out the second row and third column, what we end up with is another, the 2 by 2, which is 3, negative 1, 7, and 1. When we take the determinant of M23, it is going to be 3 times 1 minus 1 times 7, which is going to equal 3 minus 7, which is 3 plus 7. We get 10, so that's our determinant. And now our cofactor, A23, that's equal to negative 1, and raised to the power of 2 plus 3, the row plus the column, times our determinant. I'll just go ahead and put that here. Okay, minus 1 raised to the 5th power is minus 1, so you end up with minus 10. So once again, we have our matrix, the original matrix. We knock out the second row and third column because we're interested in the M23. And we have a matrix. We take the determinant of that matrix, and then from that, we derive something called the cofactor. So it's the cofactor that's actually going to be the real important thing that we continue to deal with. Okay. So now that we have this thing called a cofactor, as it turns out, we can use it to evaluate determinants. So before, what we did is we used the properties of the determinants to manipulate the matrix, find as many zeros as we can, maybe factor out some numbers, simplify things as much as possible, essentially put it into upper triangular form, if you remember from the last lesson, and then just multiply everything along the main diagonal. Well, this is another method of actually doing it. And again, computationally it may not be as efficient. It may or it may not. It depends on the situation. But theoretically, it comes in very, very handy. And it'll make more sense as we proceed with linear algebra. But for right now, let's just go ahead and work on actually finding a determinant using this cofactor expansion. Okay. We have a theorem. A equals A sub ij, and remember the symbol is just a shorthand symbol for the entire matrix, all of the entries. Okay. A is n by n. Okay. Then for each I, which is less than or equal to n, greater than or equal to 1, the determinant of the matrix A is actually A sub I1 times the cofactor I1 plus A sub I2 times the cofactor I2 plus so on, as many rows or columns, A sub In, oops, that should be a small a, all of these, so A sub In times A sub In. Now, there is another one of these for the columns, but again, we have a lot of indices, we have a lot of A's, lowercase, uppercase. So instead of sort of throwing out a bunch of symbolism, let's just go ahead and do an example and it'll make more sense. Essentially what this says is that I can pick a particular row or column of my choice and I can expand that matrix along that row or column, which you'll see what we mean in a minute. That's all this is saying, that you can sort of add that entry of the row and column. Let's say you pick the first row. You can take the first row entry times the cofactor for that entry, the second entry in the row, and the cofactor for that entry. Add them all together, and as it turns out, you end up getting the value of the determinant. So let's just jump into the example. We will let A equal 1, 2, minus 3 and 4, minus 4, 2, 1, 3, 3, 0, 0, negative 3, 2, 0, negative 2, and 3. So this is our matrix. Now we take a look at this matrix and we want to make things as easy as possible for us. So we want to pick the row or the column that has the most number of zeros, because that way those terms just drop out of this sum up here. They actually don't show up at all, so it makes our life a lot easier. So when I look at this, I see that the third row has 2 zeros, so I'm going to go ahead and expand along this row. Now, I'm going to give you a little bit of a checkboard pattern. In this case, we have a 4 by 4 determinant, and as it turns out, remember that minus 1 raised to the power of the I plus j? Well, as it turns out, I plus j is going to iterate 1, 2, 3, 4, 5, 6, 7, and what happens is that minus 1 becomes minus 1 plus 1 minus 1 plus 1. So instead of keeping track of all the symbolism, as far as the definitions were concerned, I'm just going to draw out the plus minus pattern for a 4 by 4 and also a 3 by 3 for you so that you know. So plus, minus, plus, minus. Basically, it's just alternating pluses and minus all the way through. Minus, plus, and you can never have a plus next to a minus vertically or horizontally. That's all it is. So you can do this for a 5 by 5, 6 by 6 if you need to for yourself. That's plus, that's minus, plus, minus, minus, plus, minus, plus. And here we have plus, minus, plus, and you'll see what this means in just a minute. Minus, plus, minus, plus, minus, plus. So these are the things that you want to keep in mind when you do your cofactor expansion. Okay, so now we've decided to actually expand this along the third row. So here's what the expansion looks like. Now, I'm doing 1, 2, 3, 4, so I'm going to have 4 terms. Well, my first term over here is a 3, and if I go over here and if I take a look, I see that this is a positive. So that means that whatever term is there, in the end, I stick a positive sign in front of it. So in this case, it's going to be a positive, and I like to actually put my positives in front of my positive values. It's just a habit that I have. It's up to you. Negatives, of course, you need. Positives, you don't necessarily need, but for me, it helps keep things consistent and balanced. So 3. Now, we said that you're going to expand it along this, and the cofactor is, if you erase that row and erase that column, what you're left with is this number, this number, and this number. A 3 by 3. So let's go ahead and 2, minus 3, 4, 2, 1, 3, 0, minus 2, and 3. Okay. Now we move to the next one. I'll go ahead and write, well, actually, no, I won't write out. Because this is 0, it's just going to be a minus 0. This is 0, so it's going to be a plus 0. And now our last term, minus is here, we put that there. This is minus 3. Now we knock out that row and that column that's in, and we're left with 1, 2, negative 3. Minus 4, 2, 1. Two, 0, negative 2. So now what we have to evaluate is this thing right here. Okay. We've done a cofactor expansion. We chose our third row because it has a couple of zeros in it. We took this entry times the cofactor of that. We took, if we were to actually write out this one, we would knock out that entry and then that entry, and then here this one. We took this entry times its cofactor, and now we have this. So now we have a 3 times a 3 by 3, a couple of zeros, and a negative negative 3 times another 3 by 3. So now let's evaluate this, and we'll put everything together. Go back to my black ink here. I'm going to rewrite what it is that we had. So we had 3 times 2, negative 3, 4, 2, 1, 3, 0, negative 2, and 3. We had minus 0, we had plus 0, we had minus a minus 3 times 1, 2, negative 3. Again, with linear algebra, there's a lot of minuses, pluses, and numbers floating around. I like to write everything. I don't like to do it in my head. And for example, I don't turn this into a positive 3 as I'm doing it. I wait until the end so that I make sure that as I'm going down the list, every symbol that I have is completely explicit and clear, not something that I've forgotten. Minus 4, 2, 1, 2, 0, minus 2. Okay, so let's go ahead and expand this one. Now this one, we can probably do, we can expand it along this column or this row because it has a 0 in it. It doesn't really matter which one. Let's go, you know what, I think I'm going to go ahead and take this row. Red. I think I'm going to go ahead and expand along that row. So I've got the 0 is gone, so I have a minus 2. Now I go back to my pattern. Let me rewrite my pattern here so that I remember it. For a 3 by 3, it's plus, minus, plus, minus, plus, minus, and plus, minus, plus. So here, it's going to end up being minus 2 times, and when I knock out that row and that column, I get 2, 4, 2, 3. 2, 4, 2, 3. And then I have this entry right here, the 3. Well, that's a plus sign, so I put a plus sign. I put the 3, and now I eliminate the row and the column that belongs to, and I'm left with 2 minus 3, 2, 1. Okay. That is going to end up equaling 2 times 3 is 6. 6 minus 4 times 2, that's minus 2. Well, okay, so this determinant is minus 2. Minus 2 times minus 2 is 4, times a minus 1 is minus 4. So that's why I want to keep track of everything, and I don't want to do it in my head early on. I want to see every negative sign and every positive sign. Here we have 2 times 1 is 2. Minus a minus 3 times 2, so minus a minus 6 is 8. 3 times 8 is 24. positive 24. So this equals 20. Okay? So this thing right here, this determinant, is equal to 20. Now we'll do this one. Okay, that'll be our number. Let's call this, so we'll call this number 1. That's our first determinant, number 1. And we'll call this number 2. So now we're going to do the second determinant. Now we take a look, and same thing. We have a 0 in here, so let's go ahead and expand it along this. So we look down here, it's positive, so it's going to be 2 times. Well, we eliminate the row and the column that that belongs to. 2, negative 3, 2, 1. 2, negative 3, 2, 1. The 0 doesn't matter, but I'll go ahead and put it in anyway. Well, actually, you know what? We don't need it. It's not that important. And then the minus 2 over here, it is positive, so minus 2. I like to write it that way. And when I eliminate that row and that column, I'm left with 1, 2, negative 4, 2, 1, 2, negative 4. Negative 4, 2. Okay. And when I do this multiplication, I end up with 16 minus 20 is equal to negative 4. Now, these are just the square determinants. Notice I haven't taken care of the 3 and the minus 3, so now I'm going to do that. So I have, my final answer is 3 times the 20. Okay? Now it's minus 3 times minus 4. And when you do all of that, you end up with 48. Again, this last part, let's do it again. I got 20 for this determinant. I've got minus 4 for this determinant. But I had the 3 and the minus 3 from before. So I brought those down. 3 times the 20, minus sign is here. Minus 3 is here. And the determinant that we solved for this one is minus 4. Make sure you keep track of all this. A single minus sign will make you go in an entirely different direction. That's why it's really important to write everything out and do it this way. It is the best way to do it. Be as clear and explicit as possible. Don't do anything in your head along the way. Okay. Let's see what else we have here. Let's talk about the inverse of a matrix by cofactors. So what we just did was introduce cofactors. We solved a determinant by cofactors, and now we're going to see if there's a way to actually find an inverse by cofactors, and there is. So, so far, the way that we've been doing inverses is actually a very, very wonderful computational method. So if I have some matrix A, which is n by n, I actually end up forming the augmented matrix, if you remember. Okay, let's just put that there. I ended up forming this matrix, and then I subjected this matrix to Gauss-Jordan elimination in order to end up with a reduced row echelon form. And if it actually has a matrix, if it has an inverse, that A turns into the identity matrix, and the identity matrix turns into some matrix B. Well, as it turns out, that B is the inverse. Wonderful procedure to do. It always works. If it doesn't turn out to be an identity matrix, in other words, if you get like a row of zeros or a row of inconsistency, then that just means that the identity matrix, that means that the inverse doesn't exist. Excuse me. We're throwing around all kinds of terms. Identity matrix, inverse, determinant. Try to keep them all straight. I'll try to keep them all straight. Okay. So now let's introduce another way using cofactors. Let's start with a definition. Okay. We will let A equal be the matrix ij. Okay. And it is n by n, of course. Well, we'll write it out. N by n. Then the n by n matrix, okay, ADJ of A, it's called the adjoint. of A is the matrix whose I jth entry is the cofactor Ji. In symbols, it looks like this. Adjoint of A, and sometimes you'll see parentheses around it, sometimes not. A11, A21, AN1, A12, 22, A1N, all the way down to ANN. Okay, very, very careful here. Let's go through this very, very carefully. The first thing that I'd like you to notice, so we have, if we start with some matrix and we want to form the adjoint of that matrix, okay, what we do is, let's say, for example, for that entry, okay, for the first row, first column entry of the adjoint, we actually take the cofactor of the entry for the original matrix. But what's interesting is notice that the entry for the first row, second column, is the adjoint for the second row, first column. Everything is transposed. So what you end up, the order is reversed here. So when you're going along a matrix and you're going along the rows and columns of that matrix, when you form the adjoint, you're actually going to reverse the order. So now we'll give you an actual procedure, the method for doing this properly so that you'll always end up getting it right. Okay. So, best method for forming the adjoint of A, very, very simple. 1, form the cofactor matrix of A, and then, in other words, the matrix of the cofactors of A, and again, it'll make sense when we do an example, and then just take the transpose. That's the best way to do it. Just take the transpose. Instead of trying to do each entry and trying to remember where it goes, just do it for the matrix straight and then just flip it along the main diagonal. Okay, let's do an example. So we have our standard matrix A. It is 3, -2, 1, 5, 6, 2, 1, 0, -3. Okay. And just to remind ourselves, I'll go ahead and put plus, minus, plus, minus, plus, minus, plus, minus, plus. Our pattern. Okay, so now we're going to actually find the cofactor for this entry, this entry, this entry, for all of the entries. And then we're going to put them into a new matrix, those entries, and then we're going to flip it. Okay, so A11 equal to, well, remember the cofactor, plus, and when you knock out this row and that column, you're left with 6, 2, 0, -3. 6, 2, 0, -3. When I take the determinant of that, it's 6 times -3, which is -18, minus 0, plus. So it's -18. That's that entry. Now we'll go to, where should I do it? I'll do it over here. Okay, no, it's okay, I'll do it over here. A12. Okay, so this is the cofactor for the entry, first row, second column. So it's a minus sign, right? So minus, and then if I knock out this row, this column, first row, second column, I get 5, 2, 1, minus 3 left over. 5, 2, 1, minus 3 left over. 5 times minus 3, minus 15, minus 2 times 1, minus 17, minus a minus 17, I end up with positive 17. So again, arithmetic is a real issue here. Let me erase some of this here. Okay, I want to actually be able to do it right underneath. So A, 1, 3. So we're still in the first row, third column. That entry is that. Okay. It's positive. When I knock out the row and the column that entry is in, I'm left with 5, 6, 1, 0. 5, 6, 1, 0. Okay, and the 5 times 0 is 0, minus 6 times 1, plus minus 6. Okay, now let's move to the second row. So now we want to find A21. A21. Well, it's a negative sign. When we come over here, the entry is a 5. We knock out that row, that column, we're left with minus 2, 1, 0, negative 3. Minus 2, 1, 0, negative 3. That determinant is equal to negative 6. We want to do a 2, 2. Positive. Over here, when we knock out that row, that column, we're left with 3, 1, 1, negative 3. 3, 1, 1, negative 3. This is negative 9. Minus that, we get a negative 10. Okay. Let's go to A23. A2. Actually, you know what? I am going to, so that we actually have something to refer to, I'm going to rewrite the original matrix here. And yeah, that's not a problem. So A, our original matrix was 3, negative 2, 1, 5, 6, 2, 1, 0, minus 3. We want to be able to refer to it. And we said the last thing that we were working on was the cofactor for the second row, third column. Okay, so we go to second row, third column here. It's a negative, plus, minus, plus, minus, plus, minus. And then when we knock that out and that out, we get 3 minus 2, 1, 0. 3 minus 2, 1, 0. 3 times 0 is 0. Minus a minus 2 is positive 2. Minus negative 2. Okay, now we'll work on the third row, a 3, 1. Positive, negative, positive. So it's positive. When I knock out that row, that column, I'm left with negative 2, 1, 6, 2. Negative 2, 1, 6, 2. When I solve that, I get negative 10. I have a 3, 2. So positive, negative, positive, positive, negative, negative. When I knock out that row, that column, I'm left with 3, 1, 5, 2. I end up with negative 1. And my last one, the cofactor for the third row, third column, it's positive, negative, positive, positive, negative, positive. It is positive. When I knock out that column, that row, I'm left with 3, negative 2, 5, 6. 3, negative 2, 5, 6. And I should end up with 28 if I have done my arithmetic right. Okay, so now we can put all of these numbers into a matrix. We can form, we start with, let's call it the, well, we don't have to call it anything, the cofactor matrix of A. Okay, that's our first step. We form the cofactor, then we take the transpose. So we put all of the numbers that we got in. Minus 18, 17, negative 6, negative 6, negative 10, negative 2, negative 10, negative 1. It's this one, the last one we did, and 28. And now, after we do this, we want to take the transpose of this. Okay? So let's go ahead and take the transpose, and we end up with a final matrix which looks like this. So it's going to be negative 18, negative 6, negative 10, 17, negative 10, negative 1, minus 6, minus 2, and 28. So I started with a matrix. I found the cofactors for each entry, numbers essentially, and I take those numbers and I put them into, and I form a new matrix. Okay. This is my cofactor matrix, and then that matrix that I got, I take the transpose of that, and I end up with, this is my adjoint. It's a bit of a process, but this is how you do it. Okay. Let's see here. Now let's use our adjoint to come up with the actual inverse. So let me see. We will let A be n by n. Then, let me write out the theorem and then we'll fiddle with it. A times the adjoint of A, okay, equals the adjoint of A times A is equal to the determinant of A times the identity matrix. And the only reason the identity matrix shows up here is that here we have two matrices multiplied by each other that gives you a matrix. Remember, the determinant is a number. So if ever I want to turn a number into a matrix, I multiply it by the identity matrix. It just means multiplying everything on the main diagonal. So it's a way of converting a number to a matrix. That's the only reason that it shows up here. So this theorem says that if I take the original matrix and I multiply by its adjoint, or if I do it the other way, if I take the adjoint and multiply by the original matrix, they're both defined because it's just n by n either way, I end up actually with the determinant times the identity matrix. Now, again, since this is an equality, anything that I do to one side, I can do to the other and maintain the equality. So let's just fiddle with this a little bit. Let's take this one, and let's take that one. I just picked randomly an order, so let's just go ahead and knock this out. The equality is still retained, but it doesn't really matter. I'm going to multiply both of these by inverse on the left. So when I do that, the equality is retained, right? So the A inverse times adjoint of A equals A inverse times determinant of A times the identity matrix. Okay, so now, well, A inverse times A, remember, associativity, A inverse times A is just the identity matrix. So I end up with the identity matrix times the adjoint of A is equal to A inverse times the determinant of A times the identity matrix. And again, the identity matrix, as far as matrices is concerned, it is the identity. In other words, it just acts like a 1. So when we do 5 times 1, we don't necessarily put that 1 there, we just say it's 5. So for all practical purposes, we can ignore these. And now, since determinant is a number, I can divide both sides by that number. Now remember, I can't divide by a matrix, but I can divide by a number. The determinant of A. So we can ignore this and this, they're there. So now, the determinant, those cancel, and I'm left with the A inverse is equal to the adjoint of A divided by the determinant of A. This is my formula. So now, if I'm given a matrix And if I want to find the inverse, I can do it one of two ways. I can go ahead and set up that augmented matrix and convert the matrix to the identity if it is such, and the identity matrix will turn into the inverse if it exists. If not, then the inverse doesn't exist. And here, or I can find the adjoint matrix, which again, I can do very, very simply with mathematical software. It's not a problem. And I can divide it, oops, I forgot to put the A. And I can divide it by its determinant. Well, notice something really, really interesting here. The determinant is a number. Well, if the determinant is 0, we know that division by 0 is not defined. So in this particular case, if you know the determinant of a matrix is 0, that automatically tells you that the inverse doesn't exist. So now we're going to actually write that as a theorem. Okay, A is non-singular, and remember non-singular meant invertible. It has an inverse. If and only if, which means is equivalent to, the determinant of A not being 0. Excuse me. So if I'm given a matrix, and if I take the determinant of that matrix, again with math software or however I want to do it, if the determinant ends up not being 0, I know the inverse exists. If the determinant is 0, this formula that establishes a relationship between the inverse, the determinant, and the adjoint tells me I can't divide by 0. That tells me that the inverse doesn't exist. Okay. Now, at the beginning of the lesson, I mentioned that computationally this is probably not the best way to go about finding an inverse, but it is kind of interesting from a theoretical point of view to see that if you start with some inverse, and if you end up sort of fiddling with the numbers, this square array of numbers, and you end up with something called an adjoint, where if you divide by its determinant, it ends up being related to its inverse. This is what we look for in mathematics. There is no reason in the world to believe that this is true. There's nothing in intuition to lead you to actually investigate that this would be true. But when you start fiddling with things, when you start sort of following logical conclusions and seeing where particular mathematical derivations lead you, you end up with something really extraordinarily beautiful. The adjoint, a matrix, its inverse, its adjoint, and its determinant are actually related. That's very, very strange. And again, there's no reason it should be that way, but there it is. We've elucidated a fundamental fact about nature, a fundamental fact not about mathematics, but about how numbers behave, how collections of numbers behave in this case. Okay, let's go ahead and add to our list of non-singular equivalences. You remember last time we have a list where we said if A is non-singular, meaning invertible, we can draw other conclusions that are equivalent to it. Like we said before, we're going to continue to add to that list, and the list is going to get rather long, but it's going to be a very powerful list. Okay. So we have A is non-singular, invertible. Okay. That's the same as saying that if I take A and multiply by some variable matrix, that the system, the linear system, the homogeneous system, AX equals 0, has only the trivial solution. Okay, so if it's invertible, if it has a matrix, the AX equals 0, the homogeneous solution, only has the trivial solution. So just by knowing that something is actually invertible, taking a determinant and realizing that the determinant is not 0, I can tell you something about the homogeneous solutions. I've made a qualitative statement about it. I don't have to worry about trying to finding it because it tells me it's only trivial. It's not worth finding. A is row equivalent to the identity matrix, meaning with those manipulations of exchanging rows, exchanging columns, multiplying one by the other, I can convert it to the identity matrix. AX equals B has a unique solution for every B. So if I have a matrix, an n by n matrix A, and I know that the inverse, I know that the determinant is not 0, that means the inverse exists. I know that the non-homogeneous solution, that there is actually a unique solution, not an infinite number of them, and not no solution. And of course the last one, which is the one we did today, if it is non-singular, invertible, that's the same as the determinant not being equal to 0. Okay, let's do an example. Okay. we want to compute the inverse of the following matrix if it exists. So let's try blue ink. How's that? So we have our matrix 4, 2, 2, 0, 1, 2, 1, 0, 3. So we have a 3 by 3 matrix. First thing we want to do is find its determinant. Okay, so the determinant of A, I'm going to do a cofactor expansion, and I think I'm going to go expand it along this column. I could do this row because it has a 0 in it, but I'm going to go ahead and expand along this column. So again, let me over here write plus minus plus, minus plus minus, plus minus plus. So when I go according to this column, the first term is going to be a plus, second is going to be a minus, which it doesn't matter, it's a 0, and it's going to be a plus over here. So the determinant is equal to 4 times, if I knock out 1, 2, 0, 3, minus 0 plus 1 times 2, 2, 1, 2. 1 times 3 is 3, minus 0. 4 times 3 is 12. This one, of course, doesn't matter. 2 times 2 is 4. Minus 2 is 2 times 2, so it is plus 2. So our determinant is 14. It's not equal to 0. So the inverse exists. Now let's actually find it using our formula. Okay, we want to form, our first step is we want to form the matrix, the cofactor of A. We want to take A, which let me rewrite it again because just to make it a little more clear what matrix we're dealing with. 4, 2, 2, 0, 1, 2, 1, 0, 3. We want to form the cofactor, then we want to take the transpose of that. Okay, so let's go ahead and do our cofactors. A1, 1. So I go up here, A1, 1. That means I knock out this row, this column, and I'm left with 1, 3, 2, 0. And the determinant of that is 1 times 3 is 3, minus 0 is 3. It's positive. A1, 1 is 3. A1, 2. I go up here, first row, second column. I knock that out, I knock that out. I'm left with 0, 2, 1, 3. Okay? And since it's going to be a negative, 0 minus a minus, this is minus 2 is the determinant, but I have to stick a negative sign in front of it, so it ends up being plus 2. A1, 3. I knock out that column, that row, I'm left with 0, 0, 1, 1. So it's 0 minus 1 is minus 1, and it's positive, so that's equal to negative 1. A2, 1. I'll do one more, and then we'll just write down what the others are. So now we are on the A2, 1, which is second row, first column. I knock out this column, knock out that row. I'm left with 2, 2, 0, 3. 2 times 3 is 6. Minus 2 times 0 is 6. So 6 minus 0 is 6. However, we're using this cofactor, which is a negative, so it's minus 6. And then when we continue along this fashion, we get A22 equals plus 10. We get A23 is equal to a positive 2. A31 is equal to a positive 2. A32 is equal to a negative 8. And A33, I'll actually do this one. 3, we're down here. Knock out this one, knock out that one. I'm left with 4, 2, 0, 1. 4 times 1 is 4. Minus 0 is 4. Positive. It's positive 4. Okay, so now I'm going to actually put this, I did it like this because these are the numbers that you're going to arrange. Your matrix is actually going to be 3, 2, negative 1, negative 6, 10 plus 2, 2, negative 8, and 4, the cofactor matrix. So let's form that. So our cofactor of A is equal to 3, 2, negative 1, negative 6, 10, 2, and we have 2, negative 8, and 4. Now we want to subject that to transposition. And what we end up with is, just flip the rows and the columns, 3, negative 6, 2, 2, 10, negative 8, negative 1, 2, and 4. This is our adjoint. Okay, and now we said that our determinant of the original matrix was equal to 14. We know that the A inverse, oops, wow, that was interesting. We know that A inverse is equal to the adjoint of A divided by the determinant of A. Well, we just take this adjoint, which we just got, divide every entry in there by 14. So we get 3/14 minus 6/14, 2/14. Now, I wanted to talk to you about reduction. Yes, 2/14 is 1/7, 6/14 is 3/7. It's up to you. I personally, I like to leave my numbers the way that I found them. Reducing is fine if you want to. If you don't want to, it's perfectly acceptable too. I like a degree of consistency. I don't like 7s and 14s floating around in my numbers. It just helps me. So I actually don't reduce my numbers. I know most high school math teachers would probably kill me for that, but there it is. Okay, so 2/14, 10/14, minus 8/14, minus 1/14, 2/14, and 4/14. This final matrix is our inverse that we were looking for. Again, it is the adjoint of A over the determinant of A. Determinant exists, we're good. If the determinant is 0, we don't have to bother trying to find an inverse. It's a very, very nice theorem to be able to use that. Okay, we're going to close off this particular lesson with a really, really beautiful theorem called Cramer's rule. You probably remember it from your high school courses. Perhaps you didn't see it. I imagine most of you have probably seen it though. It offers a way to find a solution to a linear system that is the same number of unknowns as variables, same number of unknowns as equations. So let us write out, let me go back to my black ink actually. Let 1 x1 plus a sub 1 2 x2 a sub 1n x sub n a sub 2 1 x1 a sub 2 2 x2 plus a sub 2n x sub n, and then we go work our way down, a sub n1 x sub 1 plus all the way down to a sub nn x sub n. So this is a system of, let me put my solutions here, b1, b2, all the way to b sub n. So this is a linear system, n equations, n unknowns, m by n system. Okay, the theorem says if the determinant of A, and the determinant of A is just the coefficient matrix. In other words, I take all of these coefficients and I put them in matrix form. Okay. If the determinant of A does not equal 0, then the system has the unique solution x1 is equal to determinant A1 over determinant of A x2 equals determinant of a2 over the determinant of a, etc. x3, x4. Okay, and let's finish this off where a sub n is obtained from A by replacing the nth column of A with the vector B, which is the solutions. And again, it'll make sense when we actually do an example here. So we have the following system: minus 2x1 plus 3x2 minus x3 equals 1. x1 plus 2x2 minus x3 equals 4, and minus 2x1 minus x2 plus x3 equals minus 3. Okay, let's do our matrix A. It is just the coefficients. Let me do it in red here. So we have minus 2, 3, minus 1, 1, 2, minus 1, minus 2, minus 1, and plus 1. Good. And let's do our B, our vector B, which is just this right here, 1, 4, 3. Okay, so my x1 is going to equal, now when I take the determinant of this, let's actually go ahead and write out what we have. I'm not going to go through the process of it. I use mathematical software, and the determinant is minus 2. Okay, so now when I take A, let me erase this here. A1, I get A1 by replacing this first column, 1, with that number. So 1, 4, 3, with this whole vector, I mean 3, and then 3, 2, negative 1, minus 1, minus 1, 1. Okay. When I take the determinant of that, I end up with minus 4. Therefore, x1 is equal to the determinant of a1, which is minus 4, over the determinant of a, minus 2, is 2. That's my final answer for x. a2, well, it's equal to this with that second column replaced by that vector. So I end up with minus 2, 1, minus 2, 1, 4, 3, minus 1, minus 1, 1. I subject that to determinant, mathematical software. I end up with minus 6. Therefore, x2 equals minus 6 over minus 2, which is equal to 3. And my final a3 is equal to minus 2, 1, minus 2, 3, 2, minus 1. And the third column is replaced with that, 1, 4, 3. I subject that to the determinant function, and I end up with minus 8. Therefore, x3 is equal to minus 8 over minus 2. My final answer is 4. x1 is 2, x2 is 3, x3 is 4. I form my coefficient matrix, and I take the determinant of the a1, a2, a3 matrix that I obtain by sticking the solution vector in the particular column for x1, x2, x3, and I solve it that way. Thank you for joining us at educator.com. We'll see you next time.